Here we have the same triangular thin plate of steel that we've seen before. And now we're to compute the total moment about the vertical line L at x equals 2, this green line here. So we're going to compute the moment around this vertical line instead of around an axis. So we'll start by computing dml. This is going to be plus or minus distance from the axis times the weight times dA. All right, so dml, like I've done before, I'll deal with the plus or minus in a moment. So now let's deal with the distance from the axis. So that's the distance that your arbitrary rectangle is from the axis. And remember, if we have a vertical line that we're computing the moment about, then we want our rectangle to be vertical as well. So let's first draw the rectangle here. This is happening at some x, so this rectangle is at x. All right, so this red distance here, this is x, right? And we'll say this green distance here, that's 2. So the distance from the axis, this distance right here, that distance is x. The whole distance take away, the whole distance to get there, x, maybe I can do this on here, x, that's x, take away 2, right? So that black line there is the red, take away the horizontal green line there. So that's x minus 2. The weight, again, is 50. And just like with the other examples, for a vertical line, this is going to be in terms of x. So we have dx is our width of our rectangle, the one of the dimensions in our dA. And now the height, remember this is the line x plus y equals 4, so y equals 4 minus x. Y equals 4 minus x there. Now, I just want to show you that you'll get exactly the same thing. Okay, and I guess we need to deal with the orientation, right? So let's first deal with the orientation. Okay. But what I'll show you is that if you draw the rectangle over here, we'll get exactly the same thing, and it's because of the orientation. All right, but we'll get to that in a moment. So let's deal with that orientation first. Now, thinking of this thin plate of steel as just being maybe cardboard or something, right? And then it can rotate, or maybe plywood or something. And it's only attached on the green vertical line, and it can rotate clockwise or counterclockwise. If you were to throw this piece of steel on there, it would rotate to where this side right here went into the page, and this side right here came out of the page. And that's indicated by this arrow here as positive. So this will be positive. Now let's see what happens when we draw a rectangle over here. Now d ml will have plus or minus some distance from the axis. 50 dA is going to be the same. The weight's the same. dA will be the same, so we'll have 4 minus x dx. Okay, so now that's some distance x, right? And now, so we'll, again in red, that's the distance x, right? That's this distance x here. That's in red. And in light green, this is the distance 2. Right, we'll draw that even right here. So then this distance right here from your rectangle to the axis of rotation, to the pivot axis, right? You can see that this distance here, right, this is 2 take away x, right? 2 is the whole thing, right? 2 is this whole thing, right? And we're taking away x. So that's 2 minus x. Now think about what would happen. We're told that by this blue arrow there, right, that little blue arrow, that this part rotating out of the page and this part rotating into the page is positive. But again, if we think of this triangular piece here as a piece of wood, maybe a piece of plywood, and our thin rectangle here, this thin rectangle has steel, and we throw it on there, we're going to rotate the opposite way. This part, right, this part here is going to go into the page, right? And so then our orientation will be negative. And notice that that's the same, right? So negative 2 minus x is the same as negative 2 plus x, right? We can flip that around. That's x minus 2, 50, 4 minus x dx. So you get the same thing either way. And it's because of that orientation. That's why the orientation is so important. So in either case, wherever we draw our rectangle, we get the same dml. And so now our moment about L is the integral from 0 to 4 dml. I can put this in there now. Let's see, we've got 50 x minus 2, 4 minus x dx. Pulling that 50 out and multiplying this out to get ready to use the power rule. Let's see, we've got 4x minus x squared minus 8 plus 2x dx. Let's see, that 4 and the 2 can go together, combining like terms to give us 6. When we do this math, we get negative 266.7 foot-pounds. And that's our moment about L. Now you should ask yourself, does this negative value make sense? And if you think about it, it actually does, right? Because of this orientation, right? Meaning that this side coming out of the page and this side going into the page is positive. And look how there's way more over here, right? There's way more in the out part, right? So it makes sense that the out part would actually rotate into the page, but it's supposed to rotate out to be positive, so that's why it's negative. That's why the overall answer, the moment, is negative.